Welcome. So, in this session, we are going to be covering Numpy. So, this is going to be the class on um, introduction to Numpy and basically everything that Numpy is about, especially from the point of view of just getting into exploratory data analysis. So, I'm going to call that Numpy basics. So, Numpy really is one of the most important, if not, NumPy is basically the most important um, Python library for data science, data analytics generally. And it is not really even because of uh, its usage alone. It is because if you've worked with um, within this space, if you've worked a lot on Python for data science and analytics, you're going to see that you are not like going to quite be using NumPy as much as you use some other libraries. For deep learning, you are probably using a lot of PyTorch, for example. For classical ML, you are probably using a lot of sklearn, and for EDA data wrangling, you are using a lot of pandas, and you are just coupling that a few times with NumPy. But the reason why you are going to hear from everyone that NumPy is basically the most used, the most popular, is because all of these other things that I've mentioned, all of these other libraries that I've mentioned, are all built on top of NumPy. It is very, very hard for you to find a a data library that is not built on top of NumPy. That is not something that is common. So NumPy is like the backbone of everything that happens in data science and data analytics. Now, having said that, um, let's actually look at why we really need NumPy. So our knowledge of um, there is actually a data structure called arrays. So there's a data structure called arrays, and based on the definition of arrays, in my opinion, I don't think there is an actual implementation of arrays in Python. For example, you could think of something like lists, and if you go age, let's say we have a list of age, or let's say ages, and ages equals, let's say 23, 45, 12, 34. Now if we print type age, we print type of ages, it says list. You already know this from our uh, previous classes on Python basics. Now that is just what we can do. We cannot look at all of these elements here as a collective and point to them in a way. All we can do is just look at this particular thing as a list. What I mean is we cannot figure out whether this is a list of integers or a list of floats or a list of something else. So, and the true definition of arrays, if you come to definition of arrays, so to just quickly give you an idea, it says an array is a data structure consisting of a collection of elements, values of variable of same memory size, each identified by at least one array index. Actually, the main thing that I'm looking for is that they are arrays are supposed to be of the same data type. So it says an array is a collection of items stored in a contiguous memory location. So according to that type, basically, let's say arrays meaning. If you check that, one of like the most popular definition of an array is that they are of the same data type. So elements in an array are always of the same data type. all of these definition here are not quite it. So because one of the most important thing uh, in an array is that they must be of the same data type, and you don't see. Yeah, perfect. So it says an array is a fundamental data structure in computer science and programming that stores a collection of elements typically of same type. So that particular implementation is not in list because I can come here and say boy like this, and if I run this, it says this is still a list, but now it is not a list of integers anymore because there is a string here now, and that makes it not an array anymore, right? Right. So now this particular array behavior is something that we need in data science and analytics, because then if you think about your columns, you are going to see that you are going to remember that your columns are usually of the same type. For example, if you have a column of salaries, they are usually numbers. You are not going to find names there. If you find a column of gender, they are usually just texts, strings. You're not going to find numbers there. So we need something that gives us this behavior where we can look at uh, a collection of elements as a tight unit, where we can also speak on things like their data type as a collective, not just individually. And that's what one of the things that arrays gives us. So how do we create arrays? The first thing that you want to do whenever you are working with Python is you want to import the library. So we say import numpy as np, and we run that. Now, creating arrays now. Create numpy arrays. How to create numpy arrays? So to create numpy arrays, we can do it from Python list. Let me add the subtopic here and say array creation and special arrays. Let's just say that. So we can create numpy arrays from Python lists. From So how do we do that? Let's say we have an array called A, and that's going to be np dot array, and you can pass in your list inside. So let's say we have a list 1, 2, 3. So we can create another one, say b equals np dot array. We're going to make that two-dimensional. Actually, let's go like this, and we can go 1, 2, 3, then maybe 4, 5, 6, like that. Then I can take this back up. So I can print A and also print B. Print B. So now this is array A, or we can just F string this so that you see something like that. And we can say array A, and this is, let me just take this and paste it here and control D this and say array B. So this is the first array, and this is the second array. Yeah. And really, just this is just like me trying to print so that you see what it means. So this is the first array that we created. This is the second array that we created. And this first array is one dimensional, it only has one row. And this is two-dimensional because there are two rows and three columns here. Right. So basically, that's how we create arrays just from Python lists. We do np.array, then we pass in the Python list, and it could be a list of lists also. We can create that. Right. And so to just cycle back quickly to what I mentioned earlier. So this np.array now, I can come here and check the type of this array. So if I say print a dot the type, you know, it says the type of A is int 64 because everything inside A is integers. So if I should come here and add one float there, 3.4, everything there becomes a float. So it says every single element in A is what? Float. They are all float. Right. If I should add a string, everything becomes an object. So basically, that is what uh NumPy helps us to do. Help us to not only look at each of these things as just a NumPy array, but a NumPy array of what? Right? A NumPy array of floats, a NumPy array of strings, a NumPy array of integers and stuff like that. Great. So that is the way that works. So this is how to create NumPy arrays from Python lists. Let's look at how to create special arrays. Creating special arrays. So the first one I want to create is zeros, arrays of zeros. So how do we do that? Very easy. We say np.zeros. Actually, let me just say zeros array equals np.zeros. And what you're going to pass in is the shape of what you want to get, and it's going to go in as a tuple. So you can say shape equals 2 comma 3. So I want it 2 rows 3 columns array of zeros. Let me add print here, zeros underscore array. So this is a 2 by 3 array of zeros. Another thing that we can do is we can do ones. I'm just going to copy this and paste it here again. So it's going to be arrays of ones. Let me do ones. And for ones, it's the same thing really. It's just shapes equals a tuple. Let's do 2 by 2 in this case. And what does ones returns for returns? Array of ones returns a matrix that has just one everywhere. So this is it here. So we have 1 1, and this is a 2 by 2 because we specified 2 by 2 here. Then we can also have an identity matrix. We can create an identity matrix. And the way that is going to work is, let me get this, although it's just a little different from the normal approach. We use np.I for that, and an identity matrix is always going to be a square matrix. So we don't need to pass in this shape. Only need to pass in the integer. So if I do 3, it's going to be 3 by 3. If I do 2, it's going to be 2 by 2. If I do 4, it's going to be 4 by 4. So I can come here and say identity underscore array. This is a column. This is a variable name, so you can add anything there. But the method is not np.identity, it's np.I. So if I run that, this is our identity matrix. Basically, an identity matrix is a matrix that has these ones like this in the leading diagonal. And it is important in concepts like eigenvalue computation and stuff like that. So yeah, that is how we create identity matrix. And something I want to point out is np.ones and np.zeros. They are 0 and 1 way of doing np.full. There is something called np.full, which is our way of creating. Let me show you. Creating a matrix of same element. So if I should just copy this whole thing. Nope. Let me copy this one. This one is going to help, and paste it here. I can have control D, let me call it same underscore array, like an array of same number, and it's going to be np.full. And what np.full takes is firstly the shape, and second thing is the fill value. So fill underscore value, and let's say I want it to fill it with 5. So if I should run that, can you see it creates an array of 5 that has a 2 by 2 matrix. If I want it to be 2 by 3 matrix, it's saying, okay, create an array of 5 everywhere and fill it up with 5. So there are a lot of things you can do really, You can also do ranges, right? You can do ranges. So for example, I can do something like, okay, let me add this ranges. You can create an array in a range. So if I want to say let's let's say under 10 array, I can do np.arange. And what that takes is the start. It's just like your normal range in list, which comes with Python generally. So you're going to get your start, your stop, and your step. So in this case, our start, let's say I want to start from 0, I want to stop at 10, I want to take steps of 2. So we say print under 10 array. So we see 0, 2, 4, 6, 8. And if you do not pass step 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and like every other thing in Python, it stops at the upper boundary, right? And yeah, that is it. So let me just add 0 here, just for the 2 here, just for the sake of it. Now, another thing that we could do is we could actually do np dot line space. You could do np dot line space. And what np dot line space does, let me show it to you, is this. We can do, let me say, np line space. And in here, the way this works is that it returns like evenly spaced numbers over a specified intervals, right? And the interesting thing is we could, for np.a range and normal range in Python, you can't get decimals. So this actually help you to do something like that. So for example, if I should do 0, comma 1, you know, just like it is listed in the documentation here, right here. So if should say 0, comma 1, comma something like 5, and I run that, we get 0, 0.25, 0.5, 0.75, blah blah blah. Basically, we say from 0, just like I did earlier, 0 to 1. Like the start is 0, the stop is 1, and the step is 5. So in this case, if I should do something like that with np.arange, something like this with np.arange, it's not going to work. I should come here and say np.arange, then I do 0, 1 to 5. It's not really going to work. Why? Because this particular step is bigger than the uh the stop, right? That's the reason. So that is the reason why it didn't work. But line space, or I don't know, lane space, some people call it lane space, allows you to do that. So it just really puts that particular 5 units within this particular place. And that's why you have 0, 0.25, 0.5, 0.75, and 1. Perfect. So we can actually see one more thing, which is under this array creation before we move on to arithmetic operation. So we can look at how to create random arrays. We can look at how to create random arrays. Yeah, random arrays are particularly interesting in our workflow, like our day to day. When we start doing a lot of analysis, there are some situations where we just need to get random arrays. And how do we generate random arrays? We can uh, generate uniform random arrays. That is random arrays that follows uniform distribution. What is uniform distribution? Uniformly distributed using 0 and 1. So if I say uniform underscore array, that's going to be np.random dot rand And if we say, give me a 2 by 3, the shape of it, a 2 by 3 uniform array. So if I should come here and say uniform underscore ARR, so I get this particular 2 by 3 array that is uniformly distributed. It is between 0 and 1. So let me just add print here so that we can add more, right? Then the next one is going to be normally distributed. And I can just copy this whole thing and paste it here. And instead of just rand, that's going to be rand n. And I can highlight this uniform, Control D, change it to normal array. So this is normally distributed. Normally distributed meaning it has mean 0 and standard deviation of 1 approximately. And let's get integers, right? Like random integers. So how do we do that? Let me copy this, paste it. How do we generate random arrays of integers? So we're going to say integers that does not follow any distribution really. So you say Control D, random int, like this, random int array. So that's going to be random dot rand int. And rand int takes first thing is the low, the high, and the size. Like where should this particular thing start from? So let's say 3. I should be something like 9. So the all of the elements in this particular array that I want to create should start from 3 to 9. And the size of it, let's say the size of it should be a 2 by 3. And that size is going to be a tuple, I guess. So 2 by 3. And we can run that, and we see that this is a 2 by 3 array between of numbers between 3 and 9. So there are still a lot of cool things that you can do with array creation, but we don't want to spend too much time. And there is a documentation. Numpy has a documentation I can always go to. There is nothing. One thing that I believe is there's nothing anybody can teach you across a course, a YouTube video, a proper learning session, anywhere, even in the best universities, that beats what you are going to find in the documentation. So make it an habit to always go into documentation and really, really like dig deep if you need to learn something. So everything that we are learning right now, for example, array creation is here. So this is everything I've been showing you. They are all here, and you can dig deep into it and understand how it works. So all of these videos are just always like guide, something to like gently introduce you to a particular library. So now the next thing we're going to be looking at is arithmetic operations. We're going to be looking at arithmetic operations. So what are some of the arithmetic operations that we can do with the numpy array? So I'm just going to create two array. First one is going to be x, and that is going to be, excuse me, np dot array. I'm going to be creating it from a list of list. Let's see, 1, 2, 3, just something very simple. Y is going to be np dot array, and that's going to be maybe 4, 5, 6, right? So first one is addition, but I don't know if I should add comment for each one because it's obvious. So for addition, we can do x plus y, and we get 579. For subtraction, we can do x minus y, and that is element wise subtraction. Like this element minus this element minus this element minus that. Then we can have element wise multiplication, and we get 1 times 4, 2 times 5, and 3 times 6. Then we can have element wise division. So this is element wise division. And we can also have something like a scalar operation, like you can do scalar multiplication, for example. And for example, you can do print 2 multiplied by x. So this is scalar multiplication. You can do scalar exponentiation, like you just take square of each of the values. So 2 squared, excuse me. So you can, you know, take exponent. No, that's wrong. X star star 2 is what I want to show you. So 149, right? 1, 4, and 9. So 1 squared, 1, 4 squared, uh, 2 squared, 4, 3 squared, 9, something like that. So this is addition element wise. This is subtraction also element wise, and product element wise product, and this is division element wise division, and this is scalar multiplication. So another one that we will look at is, let me just call this one basics. So the next one that we're going to look at is matrix arithmetic. Let's look at matrix multiplication. And that is particularly interesting to see. So let's say we have a matrix A equals, so let's just make it very simple. I'm going to make it a 2 by 2 matrix, and 1 comma 2, then 3 comma 4. And let me just copy this whole thing and make this one B, and I can go 5, maybe 6 here. You can create anything. That's just me playing around with stuff. So the way to do matrix multiplication is going to be A with this at sign. So this at sign here is what we use to do matrix multiplication. So if I do this and run it, we get this outcome 19, 22, 43. And how does matrix multiplication work? So this row, let me make it cleaner for us to understand, but that might mess it up a bit. Let me see if I can print A and also print B. It comes out nice. Yeah, it did. So the way this is going to work is, how did we get this 19? From matrix multiplication, this row is going to multiply this column 5, 7. 1, 2, comma 5, 7. And multiply by 5, 7, 5, 7. That's what give us 19. And how did that work? 1 times 5. The way we get 19 is this: 1 multiplied by 5 plus 2 multiplied by 7. 2 multiplied by 7. So if you run that, you should have 19. Can you see 19? That's how we got this 19. And how did we get this 22? 1 times 6 multiplied by 2 times 8. So I mean, if you don't understand matrix multiplication, you probably should just quickly look that up online. Is very easy to understand, and it is central to majority of the things that you are going to be doing in data science particularly. So I actually have a video in the deep learning course that explains matrix multiplication again, gives a quick refresher. And one rule to always remember whenever you are doing matrix multiplication is that the number of rows in the first matrix must be equal to the number of column in number of columns in the second matrix. That is just the rule. If that is not true, then the multiplication cannot happen. So yeah, that is that. The next thing that we're going to be looking at is array slicing and indexing. Indexing. So just like lists, arrays can be, you can slice arrays, you can index them, but you can actually do it in a way that is way better than what is happening in lists. So let's have just some array and say my array. Then let's just do np.arange, arange, something like this, just to use it again since we've seen it before. And we can print out my array, like the full thing. So we have 0, 1, 2, 3 to 9. So if you want, like, the way you've always been slicing your list, so I can go my ARR. If I want to get 2, 3, 4, 5, that is going to be 2 to 6. So we have 2, 3, 4, 5 because this is in position 2. Python starts counting from 0, and this is in position 6. And you can also, uh, get it in reverse, right? You can also get it in reverse. Like you can do all of those negative something to negative other thing. This is slicing. And indexing will be something like my, let's print. This is the one that we should print actually. Can print this, my ARR, like this. So we can print again something like my ARR of 3. And this is indexing. And we expect this to, excuse me, indexing. So to return 3, 0, 1, 2, 3. This is on position 3. Perfect. So, and you can also like slice from back from the back. So if you do -3, that's going to print out 7. Perfect. So and you can also reverse this array and print a reverse of this array. So you can do this, my ARR. I can go this and I have your 2, then -1 like this. This is not just an array thing. It is, you can handle a normal list like this. Even a string, you can reverse it like this. So that is just to show you that everything still works the way you know them to work. But now, what are now the interesting things that NumPy brings into indexing and slicing? That is when you start working with multi-dimensional array. So let's say we have an array M, and it is, let's just say np maybe the, okay, let me show you this from scratch. So np.arange, and we do 1 to 13. And if I should run this, you see that we have 1, 2, 3 to 12 like this. Let me call it, I don't know, I'm running out of names. Let's call it matrix ARR. So I can actually display this matrix ARR now. So another thing I can do is I can actually reshape this. And what does reshape do? Reshape actually help us to like turn a particular array to a way that we want it to be. Do you understand? So I can do dot reshape, and I can pass in the new shape that I want it to be. So I could go, maybe shape was the length of this 2, 4, 6, 8, 10, 12. Okay, we can do something like 3, 4. So if I do this and I run it, shape is an invalid. Okay, what Oh, no, 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 no. That should not be a tuple. Excuse me. Should not be a tuple. Should just take these two numbers like this: the number of rows and number of columns. So if we do this, perfect. So it has turned our 1, 2, 3, 4 one thing to what? To three rows and two columns from that flat line. So I can just cut this one. I can say matrix underscore ARR, because matrix ARR dot reshape. So we now know that matrix ARR looks like this now. So let's say I want to print out, this is going to help us actually learn how to index and slice a matrix that has multi-dimension. So let's say I want to print out the element on row 0, column 0. This is row 0, column 0. This is row 0, this is column 0. So I can do matrix underscore ARR, then do like this 0, comma 0, and run that. And I have 1, which is the first element. Let me print matrix ARR again so that we can always have reference to that. So this here, this is 1, which is the element in this particular position. For lists, you are going to have to like do it twice. One box for 0, one square bracket box for 0, another square bracket box for the second 0. So that is that. Let me add this in a print to you can say returns first element. Then the second thing that we would want to do is how to maybe grab a single row. If you want to print out a single row, so let's say we want to print out this 5, 6, 7, 8 row. How can we do that? I'm going to say print matrix error, and here we're going to have 1 comma then this. We are saying grab row 1, and for rows we put the column, this column sign, we put it at the back. For columns, we put it in front. You are going to see that shortly. So say print row 1, and this is row 1. This is row 0, and this is row 2. So if we print that, we are going to have 5, 6, 7, 8 that we have here. And I can just copy this whole thing and say this. So for printing column 2, that is 3, 7, 11, I'm going to have, like I mentioned earlier, you start with the um colon, then you go 2 like this. So this is going to print column, column 2. And if we run that, we have 3, 7, 11, which is this column here. 3, 7, 11. Perfect. So also we can do something like a conditional, something called Boolean indexing. So we might want to see elements that is greater than a particular value. So we can go like print, and this is particularly useful. It has a clean implementation in pandas that you're going to be seeing in the future class. So I say print matrix ARR for where matrix ARR is greater than, let's say, 3, around that. So 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are the ones that are greater than 3 inside this particular original matrix. So that is how you slice uh, an index numpy. There are still a few other things that you can do. I think there's something called fancy indexing and stuff like that you can look up, and they are interesting too. Yes, so we are getting to the part of to the end of this course, and we need to learn two or three more things. And the first one is array attributes and methods. Okay, array attributes. You've seen some of them while we were doing this. You've seen reshape, for example. So, what is the first one I want? We are going to still be using this matrix array as our example. So, if I want to check the shape, there is something called dot shape for checking shape. That's going to be matrix error dot shape, and shape is an attribute. So returns the shape of our array, which is 3, 1, 2, 3 by 4, 1, 2, 3, 4. Then another one is dimension, dim. Then we can say matrix dot, number of dimension. And if we run that, it says 2 because this is two dimensional, just as rows, columns. Then we can check the size of it, the size of an array size, and that is going to be matrix ARR again. Dot size, that should be 12. Yeah, 12 because 3 by 4. How many elements do we have in there? 12. Then the type, you've seen the type, you've seen reshape. And okay, another interesting one that we can look at is transpose. Transpose. So to transpose a matrix is to flip the matrix. For example, this is what matrix ARR looks like. This is what matrix ARR looks like. So we can F string it. Let me remove this, Control X, and say F string matrix underscore ARR. Is it what it looks like? Right, this is what it looks like. So let's see the transpose, what the transpose is going to look like. So I can print this and say matrix ARR transpose. It's going to look like something like this. So I need to just click dot T, capital T. And transpose is a concept in matrices that has extensive application. When we are computing inverse, when we are when we want to solve system of linear equation the matrix way, a lot of application for transpose. So if we run this, so it just flips, like I said earlier, it flips the matrix in a way where the rows in the original matrix turns to the columns. So the 1, 2, 3, 4 that goes like this comes like this: 5, 6, 7, 8, 5, 7, 8, 9, 10, 11, 12, 9, 10, 11, 12, like this. So that is some of the things that we can do with some of the attributes. There is dot d types. You've seen that. You've seen dot reshape. There is dot flatten to turn it into a one dimensional. This is two dimensional. So if I want to turn it to one D, I can say matrix array dot flatten, and if I run that, it turns it back to that one dimensional array, right? So that is some of the methods and attributes. How many methods do you look at? Flatten is a method. I think flatten is the only method. And reshape, we've seen reshape also. So if you come to this place, you're going to see a lot of other things, right? That is here that you can actually look at, right? A lot. Okay, yeah, broadcasting. Broadcasting is actually an important concept. So let's quickly look at that. My God, the video is getting long, but broadcasting is something cool that I should show you. So let's go broadcasting. So what does broadcasting mean? So broadcasting lets array of different shapes interact with um, each other without explicit loops. You know, a way for different arrays that have the same shapes for them to interact with each other without loops. Now, the rule is that dimensions are compared from right to left, right? So if they are equal or one of them is one, broadcasting works, and otherwise you get an error. So what does it mean? So if I say, for example, a equals np dot array, and I go, um, let's have something that has maybe 3 rows and one column. So we have something like maybe one, and we have two, and we have three, like this. And then let me just copy this whole thing. Can I do that really? No. Let me just do b equals np dot array, and we have just rows, right? So let's say we have 10, maybe 20 and 30, like that. So that is going to be very, very obvious. So if I should come here and do, okay, firstly, before I broadcast, let me show you something. If I should print A, can you see A as, or if I should do A dot shape, so that is 3 comma 1, that is 3 rows, 1 column. And if I should do B dot shape, that is 1 comma 3, right? Like basically it's not even 1 comma 3, like that. So it is just, in this case you have uh um 3 columns basically, right? Now if we want to run this, if we want to like add this particular two things together, how can we do that, right? Your normal element wise addition here will not work. Where did we do that? Yeah, your normal element wise addition here is not going to work, because then they don't have the same um dimension and size and shape and everything. They don't match each other element for element. But what we can do is this: if I should say print a plus b now, it's going to broadcast. Can you see? So what has happened is that for each one of them, we have the addition has happened. So we have 1 plus 10, 11, 1 plus 20, 21, 1 plus 30, 31, 2 plus 10, 12, 2 plus 20, 22, 2 plus 30, like that. So that is what broadcasting means, right? So yeah, let's look at, I just saw that in the doc. I feel like I don't want to keep coming to the doc, but you've just seen now that docs are really, really important for you to go to. There are a lot of cool stuff there. Now let's look at linear algebra and some statistics with numpy. So just basic things. In fact, for linear algebra, we're only going to be looking at dot products, inverse, determinants, and that's all. Those are like the very, very important concepts. So I'm going to say linear algebra. There are still more stuff that you can check yourself. So we're going to look at don't let me do that, just linear algebra. So let's say we have two matrices, and A is going to be equals np dot array, and we're going to have 1 comma 2, then we're going to have 3 comma 4. Then we can come here and say B, let's do capital B also, np dot array, and that is going to be 5 comma 6. Great. So first thing is dot product. So if we do np, let's print out np dot dot, and that's going to return like the dot product of those two matrices, those two arrays. So if we run that, we have 1739, right? That's the dot product, and I've explained this in a little way earlier at the top. So the other one here is going to be, let's say we want to get the inverse of this matrix. You don't get inverse of two matrices together, it's just going to be inverse of one matrix. So the formula for inverse is, I think, adjoint over determinant. Inverse, just to show you, of a matrix, and it has a lot of very nice applications. We use it to compute system of linear equation, we use it to solve OLS. So the formula for that is adjoint over determinant, A inverse, um I don't know. Yes, this is what I mean. So adjoint over determinant. So that's what they have here. They said 1 over determinant. This is like a very long way of writing it. This like the reciprocal of the determinant multiplied by the adjoint. So if you multiply this basically adjoint times one adjoint all over determinant. So and it has very very extensive application in computation generally. So we say inverse, and we come here and we say print. If we want to find the inverse of this a, so I can say print np dot lin arch like this, and that's dot inverse, I think. Yeah, dot inverse of a, and it is going to print out this is the inverse of a. Then determinant of a, determinant also has a lot of application, a lot. In fact, in computing inverse, like I showed you earlier in the formula, you need determinants also. So that a determinant of a 2 by 2 matrix is just cross multiplication. So that is fairly easy. So that is negative 2,0,0,4. Cross multiplication with subtraction, by the way. So if I should print out a like this, just show you how that happened. So the way you got this negative 2.000 is 1 times 4, 4 minus 2 times 3, 6. So this is how you got this. But this precision thing came into it. So yeah, that is that. There is eigenvalues, there is a lot of other things that you can get. Just check the doc. And lastly, what we are going to check out is statistics, which I'm guessing some basic statistics, which I'm guessing is one of those things that is really important for particularly data analysis and data science also. So statistics. So we have some statistical methods that we can use. So for example, we can have mean. Let's see if we have some. Okay, let's create a new one. Let's call it data equals np dot array, and we can have one, two, three, maybe a 2 by 2, a 2 by 3. I like 2 by 3 matrices for some weird reasons. And yeah, we're gonna say data dot sum, that is going to return sum. So it adds up everything. Excuse me. This adds up everything. Then you can do data dot mean. I mean, they are quite obvious. And this is just going to return the arithmetic mean. You can print data dot std, standard deviation, which is going to measure the distribution of the other data points about the mean. Data dot variance, the square of standard deviation. Then we can have data dot minimum, just the standard thing if you've learned some like SQL and stuff. Then we can have data dot max. I want to run the whole thing together to save time. Data dot max. Yeah, basically that's everything that I think I can remember off the top of my head. So this is 21 sum 3.5. Let me print data itself so that you can relate to it properly. Great. So 21 sum of everything here, 3.5 average of everything there, 1.709 standard deviation of everything, 2.91 square root of standard deviation, minimum 1, maximum 6. But for this minimum and maximum, we can actually get row max, column max also. So for example, if I should do minimum axis equals 0 and I run this, so it's showing me the smallest rows, and I can do things like for axis equals 1 for column. That's going to be 1 and 4. This column is the max, is the minimum, and you can do the same thing for max also if you want. So yeah, that is a quick rundown of NumPy and everything that you need to know about using NumPy as you know someone that's just getting into data science and analytics. So yeah, that's that. See you in the next one. And in the next one, we are going to be looking at pandas. Bye.